Okay, so we'll go ahead and get started. One announcement, your exam for Module 3 opens today at 2:15, 30 questions, 5 bonus questions. The bonus questions are relating to a sequence. There's a table with reactions. You assign a number, then generate a sequence from those numbers, and those are the responses. So you have to order the reactions in the right way to get the desired outcome. My advice on that, look at the product, identify the functional groups, then sort of associate that with the reaction transformations. Nothing terribly complex, just 2 or 3 digit responses. So you have 24 hours to do that. It closes tomorrow. Again, if you forget to do it, your 60 points moves into the final exam. So just consider that. So we're going to continue on with NAS, so nucleophilic acyl substitution. Substitution, that is the primary mechanism for the oxidation state 3 functional groups. So we said that, let me highlight in red here. So that's the acyl part. And then in blue, that's the part that's being substituted. So you can look at that part of the molecule and determine from the heteroatom what it's coming from. So that comes from an alcohol. So starting with an ester and then a metal hydroxide. So say sodium hydroxide. You can use any of the group 1, lithium, sodium, potassium hydroxides. That will do a reaction called saponification. So saponification is, due to the reagents, it's a basic medium. So in the mechanism, we have to show neutral or negative charges. And so that generates the metal salt. So metal, just use a different term here, metal carboxylate. So historically, those were used in soaps, and that's the reference to Fight Club. They were making soap. So once you have that, you can then reprotonate it. So you adjust the pH. So lower pH less than 4, say with HCl, and that gives you the acid back. So again, the names matter. When we say saponification, we mean base-promoted hydrolysis. And we'll show that mechanism. It's more straightforward than the Fischer esterification, which was acidic medium. And then I'll just show the alcohol byproduct. So we're starting with hydroxide, so negative. That means everything else we show is either a negative oxygen or a neutral oxygen. So hydroxide will attack the carbonyl, that's the addition part of the NAS. And then the carbonyl oxygen becomes negative, and it's balanced off by sodium, which is positive. So through that addition, the hybridization changes to sp3. That's the tetrahedral intermediate. And so what happens next is the elimination part. So the negative charge will reform the pi bond, so that drives it. And now we're going to eject out the leaving group. So that happens to be, so that the negative or the conjugate base of ethanol, so the alkoxide. So notice at this point, you've generated a carboxylic acid, but you also have this base present. So the acid has a pH of 5, so that base will deprotonate it. So pH 5, and then the alcohol has a pH of 16. So at this point, the arrow is a one-way street. So that's the driving force for it. And so as I said, that's the metal carboxylate. If you wanted to isolate the actual acid, then you just have to adjust the pH. You can do that in the same flask by adding in acid. So again, saponification is basic media. Any questions? Yeah.
Should this reaction proceed if it was an acidic medium?
Well, that would be the Fischer esterification.
Oh, okay.
Yeah, I mean, you could use like acidic water. You would end up with a carboxylic acid. It wouldn't go through like an carboxylate. So yeah, you can still hydrolyze with water and acid. So that's kind of the reverse of the Fischer esterification. So as I said, the carboxylic acid is really the starting point to make everything else. But the OH as a leaving group from the acid is not a very good leaving group. So really we have to take the acid and convert it into something else first, and then from there we can do the other substitutions. So of the four oxidation state 3 functional groups listed, the acid halide is really the best starting material. So we're going to learn how to take a carboxylic acid into the acid halide. And the reason for that is when we do the substitution, so that part again is getting substituted. When it becomes the leaving group, so we see now it's Cl minus. If we look at the conjugate acid of Cl minus is HCl, and then we go to the pKa table and we see that that conjugate acid is it's a really strong acid. So because of that inverse relationship, the conjugate base is really weak. That means Cl minus is stable. It's a good leaving group. And the logic is, as you progress from acid halide anhydride ester to amide, the amide leaving group, this N minus, its conjugate acid is an amine, and its pKa is 38. So that's saying of the trend here, that's the worst leaving group. So we never really start with an amide and try to substitute it for something else. We're always going to start from the acid chloride and then make our derivatives. So the pKa value is really what is determining what we start with. And then we'll have some slides about why the amide functional group is so important. So this question is using the electronegativity trend, where fluorine is the most electronegative. We see that oxygen is more electronegative than nitrogen. And the question says, the carbonyl stretch of an amide falls below 1700. So of all the carbonyl functional groups, the amide's the only one that's below 1700. So why is that? If we consider this molecule, which we'll see in a little bit, this is called DMF, or dimethyl form amide. We have our carbonyl group and then bonded to the nitrogen. Oxygen is more electronegative than nitrogen. So this lone pair gets delocalized through resonance onto the oxygen. So that's through resonance. And you'll notice what happens to the pi bond of the carbonyl. So it looks more sigma bond-like. And so that's why it falls below 1700. So additionally, the CN is more double bond-like. So that makes it even harder to do a substitution of that group because this bond is stronger. So our answer for this one would be C. The lone pair of electrons on the amide nitrogen is delocalized onto oxygen. And we'll see in one of the reactions, or two of the reactions, that we can take advantage of that reactivity with other electrophilic agents. So the trend here, we know how to make carboxylic acids. OH is a bad leaving group. We'll transform it into an acid chloride, and from that, then we'll substitute any other nucleophile X to make our other oxidation state 3 functional groups. We'll do some mechanisms today. There's a really long one. I'm not going to show the whole thing. I'll let you struggle through the rest of it, but I'll get you started on it. That will help you think and practice through like proton transfers and whatnot. So the two methods to take a carboxylic acid to the acid chloride. The first one uses this reagent called thionyl chloride, SOCl2. And the second one uses a reagent called oxalochloride. And then a catalytic amount of that amide DMF. So either set takes OH to Cl. Practically speaking, we'll see from the mechanism, thionyl chloride generates a gas that's pretty corrosive, so SO2. Kind of smells weird as well. Oxalochloride DMF is a little bit more mild, but oxalochloride also smells. If you smell it, you know it's not doing good things. It smells like, like cut grass, like fresh cut grass, but in a bad way. So those type of reagents are kind of nerve agents. So if you've heard of like phosgene, POCl2, that was a nerve agent in World War I. They'd open a tank, let the gas waft across the battlefield, hoping the wind was flowing in the right direction. And so you'll see, I have one slide about sort of enzyme reactions and how things happen with like functional groups that are present on things like hormones and amino acids and how these agents work, how those functional groups are transformed into other things. So let's look at thionyl chloride, so SOCl2, and we see that below the arrow here. We have a sulfur double bonded to oxygen and then 2 chlorines coming off it. So overall, the sulfur is at a pretty high oxidation state. You have 1, 2, 3 heteroatoms bonded to it. So we're basically going to use one of those to substitute this OH to get the acid chloride. So overall, acid, thionyl chloride, acid chloride, and then how does it happen? So written here as well, as I said, we have to account for all the other atoms involved. So it generates SO2 gas and then HCl. So when you run these, you have to put like an effluent scrubber on the reaction vessel that sort of neutralizes these things and it doesn't corrode anything it comes into contact with. So we're using and that accounts for all the atoms in those reagents. So we're not leaving anything out. Everything's coming along for the ride. It's accounted for somewhere. So we have to get rid of the OH, replace it with a Cl, then account for HCl, and then SO2. So this might be a little weird, but the oxygen bearing the OH, we're not going to use that one to attack. We're going to use a resonance form. And that will help us understand some of the other mechanisms we learn. So I want to draw that resonance form. So we have one oxygen minus, the other one's plus because it's still bonded to the H. So that can be our nucleophilic oxygen, which will attack the sulfur. So oxygen attacks sulfur, we break the SO double bond. So we still balance out the negative, the positive. We'll reform the SO pi bond, so eliminate. Now the only thing that can leave is Cl minus. So really what we're doing is we're transforming an oxygen to make it a good leaving group. So we'll have the chlorine attack the pi bond. And so at this point, everything is neutral. So chlorine's added to carbon. Now this OH group, it's going to collapse back down to form a pi bond. So this pair of electrons drives the elimination. The CO bond will break. That forms the second oxygen-sulfur double bond, and then Cl minus leaves. And then we generate HCl through a proton transfer. So now with the acid chloride from that prior table, we can react that with any other nucleophile. So if it's an alcohol, that gets us back to an ester. An amine will make an amide. Hydroxide would make a carboxylic acid. So the key thing is here, you really have to make the acid chloride first to sprout off from the other functional groups. Any questions? Still see some notes being taken, so I'll wait a couple more seconds. The next reaction is, overall, it's achieving the same thing, we're just using different reagents. So again, we can see OH is being transformed to Cl, except now we're going to use this reagent, oxalochloride. And then we're using DMF as a catalyst. So when this is run, really you just take a pipette and you put about 5 drops of DMF in it. And what's nice about it, when I normally do this, you have a flask. It looks like a ball. It's called a round bottom flask. It has a neck. You put a rubber septum in, and then a deflated balloon. So you attach that through a needle, and then as the reaction progresses, the balloon fills up. So it fills with this gas. Once the balloon is pretty big, you empty it, put it back on, and see if any more gas has evolved. So when no more gas has evolved, you know it's done. So you can work it up. And so through the mechanism, you can understand what gases are formed. So it forms carbon dioxide and carbon monoxide. So those carbon atoms, maybe I'll use some colors here. You get a carbon atom from there, say that comes from CO2. And then the other one in green forms the carbon monoxide. So that reagent essentially decomposes. So it's transformed into other stuff that goes away, but the DMF still remains. It's catalytic, which means we invoke it in the mechanism, it does something, and then it returns to DMF. So I'll get started on this. I'm not sure if I'm going to do the whole thing, but I'll show you what happens, why the DMF is used. So there's dimethylformamide, and as we saw a little bit ago, the amide has a significant resonance contributor. So the lone pair is pushed on to oxygen. And so we can use that form of the DMF to react with the oxalochloride, because now we have a nucleophilic oxygen. And the oxalochloride has a good leaving group, Cl minus. So as we saw before, we'll have the oxygen attack the carbon. That will break the pi bond. So N is plus, the other oxygen is minus. So that's a nucleophilic addition. Now we're going to get an elimination. So this collapses. and then we'll eject out Cl minus. So we have Cl minus, N plus, and then what happens now? Remember, we still have to get rid of those 2 carbon atoms. So an NC double bond behaves really the same way as a carbonyl. So that's going to undergo an addition. So Cl minus attacks, nitrogen gets its lone pair back. So now everything's neutral. So that lone pair will then eliminate. The OC bond will cleave. And so this is the weird part here. That's going to form an oxygen-carbon double bond. This bond breaks, the electrons go on the carbon. And then the chlorine's ejected. So what's different now is this part right here, that's sigma bond breaking, and then chlorine leaving. That's called an alpha elimination. Normally, you're used to seeing beta elimination. So it just means that the leaving group is coming off that same carbon that's breaking the bond. So we end up with CO2 plus carbon monoxide. So those are the gases that come off. And then this is balanced off by the chloride anion. So through all of that stuff, this reagent here, that's the actual thing that reacts with the acid chloride. Or I mean the carboxylic acid. So we might run out of room here, but I'll try to get through as much as I can. So again, there's your carboxylic acid. There's the resonance form. We're showing a nucleophilic oxygen that can attack that salt. So that oxygen lone pair attacks the carbon. We break the CN pi bond. What am I doing? This is, sorry, this negative charge is not there. So that's normal. So the negative charge is on that chlorine. So I'm going to draw this one way, whether it happens this way or concurrently. I'll just show it stepwise. Let's have I want to make sure I draw the arrows right and not F it up. We'll do this. I'm going to commit. We're going to have that lone pair collapse and that eject out Cl minus.
So the chloride ion cannot attack
The H.
The carbon like earlier, like the carbon no bond with oxygen like earlier.
Yeah, so that's what I'm debating. I sort of don't want to go that route when I show it.
Okay.
Let me just get through this first, and then we'll talk about that other one. So what I was debating about was, either having that chlorine attack the carbon or that chlorine deprotonate the H. So really what, the reason I wanted to show it this way is that when this ultimately leaves, it's going to leave as DMF. So let's just have this attack. I'm running out of space here. So that attacks the carbon. The oxygen lone pair of OH collapses. And now when it breaks this CO bond, that's going to reform the DMF. And so again, that's important to reform that DMF because it's catalytic. You're only adding a couple drops. So say, for example, the oxalochloride, you normally run it with about 1.5 molar equivalents relative to your carboxylic acid. So there's an excess. The DMF is probably 0.05 molar equivalents, so it's a catalyst. It has to be regenerated. At this stage here, I know it's messy. You probably could do proton transfers and stuff, draw it some other way. But regardless of whatever way you push the arrows, you have to eject out DMF in that form. Yeah.
So I tried it out earlier when, if at that step,
So like right here.
yeah, so when the Cl attacks that bond, and then the pi bond breaks, giving the oxygen back its electrons, and then
So it would collapse back down, this goes, and then ejects out chlorine.
ejects out chlorine, and that makes
Yeah.
DMF already, right?
Yeah. So that's another way of doing it. Whether that's correct or what I wrote's correct, one of them's probably correct. I think the important thing is to note that mechanistically they're both valid proposals. And how would you prove which one's happening? Then in the lab, that can get a little bit more complex to actually prove that. Trying to think of an experiment you could do. So when you get into this about arrow pushing, as long as you understand the fundamentals, that's what's important. To prove a mechanism is very hard, and normally that's when you start incorporating isotopes into these things, because there's a field of study called kinetic isotope effects. So relative to the natural isotope versus a labeled one, you can study the rate differences. Like for example, right here, when you get these tetrahedral intermediates, that's what a lot of biochemists study, the rate of formation of a tetrahedral intermediate. So that, in a very messy slide, is oxalochloride DMF. Operationally, it's a little easier to run. The gases, you just exhaust them into the back of the hood and you're fine. So how do we know we have an acid chloride group in the molecule? We see that chlorine has 3 lone pairs. You would think, well, it has 3 lone pairs, so they should delocalize through resonance just like an amide. But they really don't do that so much. What they do is they tug more on that sigma bond, which makes that pi bond stronger. So an acid chloride, because that part of the functional group, no matter what R is, that's always the same, and their IR is almost exactly at 1800 all the time. So acid chloride, that's the good leaving groups at 1800. Amides, the bad leaving group, that's below 1700. And here we have acetyl chloride. So that's the 2-carbon variant. And we can see that the carbonyl stretch is pretty much at 1800. So if we had a bottle of acid chloride and we opened it, you would know it's reactive because the people in the back of the lecture room would smell it within about 30 seconds. That functional group is very reactive, so it will hydrolyze with just moisture. And then as you breathe it in, it's forming HCl. And you're like, man, that's not good. So you know it's a reactive functional group. So what can we do with it when we've formed it? There's your acid chloride. If you treat it with a carboxylic acid, say acetic acid, and then basic conditions, that's going to do the substitution of the chlorine for the rest of that carboxylic acid. So that makes an anhydride. And why is the base there? So it abstracts the acidic proton. So what I've circled, the H in the Cl, that generates HCl, and the base neutralizes it. So, I mean, overall it forms HCl. It doesn't form it like all in one step. You get the base abstracts the proton from the acid. The carboxylate then attacks that. You generate Cl minus, so you're formally generating HCl. So that's the anhydride. Remember, that's the functional group that's linked, two carbonyls linked by an oxygen. So it has a pretty unique IR signature, and that's the main diagnostic tool that you would use to say you have the anhydride. So in the carbonyl region, it has a doublet. So I'll outline that. You have your sort of normal carbonyl, it goes up, and then you see another one. And the reason that happens is because since you have two of them, they can stretch in the same direction at the same time, like symmetric stretching. Or if they're stretching different, that's asymmetric, and that's why you get the second carbonyl signal. So just a brief check-in about the nomenclature. So in the first column is your functional group. The second column shows you the sort of line formula if you were just typing this in Microsoft Word, what you would write. So COCl is an acid chloride, and then the name ends in oil chloride. And then you see how the different nomenclature changes based on the functional group. So if you take an acid chloride plus an alcohol under basic conditions, so that the alcohol is both the solvent and the nucleophile. So if we're using ethanol, again, under basic conditions, that transforms the acid chloride now into the ester. So that complements the Fischer esterification we talked about. It's just another way of doing it. So as a check-in about proton NMR, let's consider the chemical shift, so delta ppm of the CH2 group. So we said that was the alpha carbon. And then the CH2 group from the alcohol part. Where would you expect to see those signals on the proton NMR? A is the correct answer. So this carbon, carbon 2 that I highlighted in red. It's bonded to oxygen. So it's going to push those furthest away from 0. And then the alpha carbon, it has a carbonyl next door. So it moves it a little bit further than your normal sort of sp3 hybridized carbon. So we would call that sort of the allylic position, so the allylic region of the proton. So how do we know we have an ester in a molecule? So again, ester was the weird one because they do resemble ketones quite a bit in the IR. And so you have to use have other supporting data to differentiate the two. But the main thing is you need a degree of unsaturation and at least 2 oxygens to get an ester. So we see the carbonyl usually 1700 to 1750, but again, that's the same region as a ketone. I'm only going to show you one amine. So with ammonia, the acid chloride plus ammonia gives you a primary amide. So you can either use ammonia itself. That comes in a tank, we call it a lecture bottle. So you're handling a compressed gas, so there's safety issues. Normally, if people want to make a primary amide this way, you would just use ammonium hydroxide. So that's just ammonia bubbled into water. So if you had a primary amine, so like methylamine, and you ran this reaction, you would end up with a secondary amide. Secondary amine would give you a tertiary amide. Tertiary amines you can't use because that would generate a quaternary amide, and those are not things. Because it's just gonna, because the nitrogen at that point is positive, it would just eject out that amine as the neutral amine. So as I stated earlier, in general, amides will have their carbonyl stretch below 1700. Differentiating between primary, secondary, and tertiary amides, there's a slight or subtle thing you can look at: the number of NH bonds. So they can appear different. So a primary amide it has 2 NH bonds. So those could appear in region 1 as sort of 2 signals. And in the example shown here, this is the 3-carbon amide. So the primary amide. And what you see in region 1 is this sort of doublet. And so that looks different from an alcohol, it looks different from a carboxylic acid, so it's indicative of a primary amide. And then we see this big old carbonyl here, and I'm not lying, there's 1700 is right there. So you see that below 1700. So what would change in this part, when you go to a secondary amide, which only has one NH, you're not going to see that doublet looking thing. A tertiary amide has no NHs, so this is completely gone. But your carbonyl is still below 1700. So say you're out foraging and you let me write something in here. And you get some lysergic acid and you want to make LSD. So lysergic acid has a carboxylic acid, and then LSD is the diethyl amide. So what sequence of reactions would you do to carry out that transformation? What do you think? C. So we see in C, so there's the acid, and we're doing a substitution for the diethyl amide. So our oxidation state is staying at 3. So we need to make that into the acid chloride first. And then because we're forming a tertiary amide, we're going to treat with a secondary amine. So in essence, when, I forget who's doing this, like Hoffman or something, was making these derivatives. I mean, you get the lysergic acid from a plant or a fungus or whatever. You look at all the amines that you have in your lab and you just make different ones. And then if you're brave, you do some taste testing. And then you say, why is the wall purple now? And you say, well, it's due to this derivative. So the reason I pointed out the primary amide, so of all the amides, primary, secondary, tertiary, the primary is the only one that will undergo this reaction, where you treat with phosphorus oxychloride, so POCl3, which again, in and of itself is a pretty nasty reagent to work with. And what do you notice between the primary amide and the nitrile product? What's the difference in, say, elements that are no longer in the product?
Oxygen and hydrogen is gone.
Your nitrogen's still there. So let me highlight. So that carbon is this carbon. So if you look at the N, that's H2, then the carbonyl oxygen is O. So really what's happening is a dehydration. Overall, you're dehydrating the primary amide to make a nitrile. So through that, even though it's not a nucleophilic acyl substitution, you're still conserving the oxidation state 3. So it says you are encouraged to draw up the entire mechanism. We only have 15 minutes left and a boatload of slides to get through. So I'm not going to draw the mechanism, but I'll get you started. It relies on the resonance form of the amide. So you can see here, the resonance form already has one double bond. You got to get another one in there. You have H, H, and O you got to get rid of. That nucleophilic oxygen is attracted to that phosphorus. So you have to react that with that. Once you get that formed, the oxygen is now bonded to phosphorus. It can become a good leaving group. And then you're just doing subsequent eliminations to get rid of those hydrogens. So again, that's something that you're encouraged to be creative and think about and draw a mechanism. You can think about different mechanistic pathways. That's always helpful in your understanding of how the arrows move. So once we've formed the nitrile, so nitriles are also called cyanides. They're sort of interchangeable. It's the carbon-nitrogen triple bond. Oxidation state 3. The telltale sign is in the IR region 2. You'll have a very sharp-looking signal. It's not necessarily intense, meaning that it doesn't really go down to the baseline, but it's really sharp and it stands alone. So this is the 4-carbon nitrile. And then in region 2 here, there's that sharp signal. And again, by sharp, I mean it goes down and then immediately back up. It doesn't span a whole large range of wave numbers. So another thing does it have it on here? So MS, odd number of nitrogens equals odd parent mass. So the odd parent mass tells you there's an odd number of nitrogens. That's how you can use the IR to say, okay, there's a nitrile. Questions? So I think these are a couple of questions we'll practice with. So what's the point of all of this? If you go on to the biochemistry sequence, you'll learn about enzymes. And an enzyme is just a large organic molecule that's designed to carry out a specific reaction in your body. So the molecule shown here to the top left, so that's serotonin. We have these other names for it. So 5-hydroxytryptamine, 5-HT. You see all these different names depending on what you're sort of reading. We have a primary amine. We have a nitrogen in an aromatic ring called indole. And then we have an aromatic alcohol of phenol. See this little blob of color here? That's an enzyme. That's sort of how they're depicted. And so that's called the ribbon form. And so it's like you're wrapping a Christmas present, and you put a bow on it. Within that form, it's hard to see, but there's different colors, right? So there's a blue, there's a green. So like here in this orange, see how it sort of spirals? And then here it's like flat. So what we'll see in Module 5 is why do these enzymes do that? So overall, that's the active structure of the enzyme. The ribbon itself is just a series of amino acids bonded together through amide bonds. So we said at the beginning the amide bond was the strongest of oxidation state 3, right? So that has consequences in biological chemistry because you want enzymes to be stable, right? You don't want them falling apart or doing substitutions. So because that peptide bond is so strong, the enzymes are strong as well. So look at the name here. Aryl alkyl amine N-acetyl transferase. And then look at the product. So based on the product, does the name make sense as to what the enzyme does? So we're starting with a primary amine. So that's the amine part. All this stuff in front just tells you kind of what's acceptable to be bonded to that amine. And then this is the action. This is what that enzyme does. N-acetyl transferase. So you can think of that that's just a big old acid chloride. So somewhere within there you have this 2-carbon unit, and it's just transferring it to that amine. And so then you end up with the product, which is called N-acetyl serotonin. And so that reacts with this enzyme, N-acetyl serotonin O-methyl transferase. So O-methyl, this enzyme is supplying a methyl group specifically to an oxygen atom. So that oxygen gets methylated, and then that makes melatonin. What does melatonin do? It makes you sleepy, right? So do you know what circadian rhythm is? So it's your normal sort of daily biological clock. And so do you know why watching this at night is bad? So it disrupts this process from happening. Like specifically that blue light is interfering with this process. Then it's 3 a.m, you're watching YouTube and you can't fall asleep because you don't have enough melatonin. And so that's why they put these warm and cold light things at certain times of the day so that you behave as a normal human being and you're not a zombie coming to class, falling asleep. But essentially biochemistry it's just organic chemistry on steroids where these enzymes are carrying out the reactions that you're learning now, but they're just bigger structures to do it. So let's see. We'll finish on this. I know we're not going to get through everything, but that'll be enough to get you through the exam. So I just want to do these last couple problems so you understand the relevance of all this. The molecule shown is called pevampicillin, and it's a beta-lactam antibiotic. So Some of you probably can't take beta-lactams because you have some sort of phenotype that makes you allergic to them. And a cyclic amide is called a lactam. So this part right here, there's the alpha carbon, there's the beta carbon. So that's a beta-lactam. And these are developed because that four-membered ring has strain to it and it's reactive. So these type of antibiotics, what they do is they inhibit cell wall growth because of the reactivity of that amide. So it says how many oxidation state 3 functional groups are present? So there's 4. We have a 3, a 3, a 3, and a 3. And so of those, if we just label them, so that's an amide. That's an amide. This is an ester, and that's an ester. So in real life, a lot of the molecules have all these different functional groups and oxidation states. And then when you start designing synthesis, it can be hard to control exactly where something's going to happen. And you have to make sure that you're not stepping on some other functional group's foot if you want to do something at a certain place. So how many oxidation state 2 carbons are there? Got a 2, we got a 3, there's 2. So that right there, that's called an N-S-acetal. And then this right there is your normal acetal. So this molecule is not the active form of the drug. This is called a prodrug. It gets metabolized and then it forms something else. And so it's a prodrug probably based on physical properties of absorption, distribution, and metabolism. So the last question here, see if you can think about it in the last minute. That carbon atom indicated by the red arrow, if it's, say, hydrolyzed or saponified, you get 2 byproducts. So not including this part. You get a nucleophile attack it, and then a degradation happens. And so what's the products of that degradation? So D. When this gets attacked, you form the tetrahedral intermediate that collapses. That leaves as formaldehyde, which is methanol. And then you get that as the other product. So this whole side chain is really there to help solubility factors and all that other stuff. So it's an example of a prodrug. And the rest of this stuff is the drug. So out of time, the rest of this stuff is kind of practice. You can go through it, design some syntheses. Everything we've covered should help you on the exam though. Please don't forget to submit it 24 hours from now. We are about